Hello, Tanya Laird here, and welcome to Part 3 of Lecture 6 of ENGR 231 Engineering Statics. This is going to be the third video in the lecture, and in this final part we are going to look at finding equivalent force couple systems. So let's consider equivalent force couple systems. Now, on a bit of a review, in the first portion of the lecture, we defined what a couple is. We said, okay, it can be represented as a pure rotation, a tendency for an object only to rotate rather than any translational tendency. It can be thought of as a free vector. It doesn't matter where you place it. An object will rotate the same regardless of where a couple is applied to it. And finally, we can think of it as if you want to talk about how a couple is constructed mechanically, you can talk about how it is a pair of forces, a pair of equal and opposite forces, separated by a certain distance. And that's what we looked at in Part 1. Then in Part 2, we looked at actually how to go about calculating couples mathematically. We looked at doing more of a 2D approach, a scalar approach, or 2D either scalar or vector approach, and then a 3D vector approach. Now, for equivalent force couple systems, though, we're going to take this one step further. So, we know previously that where a force is located matters. We know this. A force is applied matters. In other words, an object will rotate or behave differently or experience different restraining forces depending on where you apply a force to it. So I'm not talking about a couple, I'm talking about applying a force to a body. So consider our generic potato body that we've considered many times before. Just a generic rigid body. And let's say it has some center of mass, a center of mass at some location. So we have a generic rigid body with a center of mass at some arbitrary point. And let's say for a minute that I had a force here. So I have a force here, and let's call this FA because it's acting through some point A. There's some point A here, and it is acting through some point A. So that's why I'm calling it FA. Now, what if for whatever reason I wanted to move this force to a point B? Let's say I have some other point over here, point B. And I want to ask myself, okay, what kind of force would or what kind of impulse, what kind of tendency would I have to put on this object at point B in order to produce an identical behavior as this force here? So think about this for a second. Let's say I've just placed an FB here. Let's say I place a vector FB on this, like so, like this. And I tell us that FB is equal to FA. So let's say I just take, let's say I craft an identical force, FB equal to FA, and I apply it at a different rotation, or a different location. Is that going to produce the same behavior in this object or in this body as FA will? And the answer is no. The reason for that is that the moment arms will be different between different points. If I look at just rotation about the center of mass, for example, I'll have a much higher or a much larger moment arm from here than from here. So I'm going to have a much reduced tendency to rotate if I move the force here than if I move the force here. So when I move the force to B, force FA to another point, the rotational tendency changes. The object experiences a different impetus to rotate. So for example, If this were truly a free body floating in space, well, then it would start rotating at a different rate. If it is something that is nailed to the ground, like in statics class, well, then the restraining forces, the forces on its restraints, those are going to be very different depending on where I apply that force. However, but only the forces that are produced by the tendency to rotate. Any forces that are resulting from the translational tendencies, the tendency to move left, right, backwards, up, and down, those will be the same. So the real reason I can't just up and move forces to one location or another is because of rotation. So the translational tendency, however, will be the same. Tendency will be the same if I move it. Will not change regardless of where I apply the force. Regardless of where I move the force to. So again, if I'm just looking at translational tendencies, if I'm just looking at, okay, with how many newtons does it want to move to the right? How many newtons does it want to move up? With how many newtons does it want to move forward or backward? Those are all translational tendencies. And if I just move this to another location, the translational tendencies don't change. It is only the rotation that changes. So if I don't care about rotation, if I don't care if it's rotating different rate, in fact, all I care about is whether it moves forward, backward, or left, right, etc. at the same rate, well, in that case, I can just say, oh, well, I can move a force wherever I want. But in terms of rotation, if I'm saying I really want to find an equivalent system, I need to have some way of dealing with that rotation. And so if I want to move a force to a different location on a body, I need to deal with the rotation or the changed rotational tendencies. To deal with or to move a force, let's just say it this way, if I want to move a force from one location on an object to another, a location on an object to another location, I must consider its tendency to rotate, or must consider its changed tendency to rotate. Or maybe I could even say to another location without changing its behavior. Without changing its behavior. I must consider its tendency to rotate, or its rotational tendencies. It will translate the same, but it will not rotate the same. Its rotational tendencies. Or I should really say its changed rotational tendencies. So, but how do I do that? This is the question I have. How do I do that? So again, I have my rigid body here, and I want to move a force. Say I have a force here, and I want to move it to here. Well, if I realize that if I move it from here to here, there's going to be a difference in rotational behavior. Now, ideally, what I would like to do is somehow cancel that out. What I'd like to do is somehow apply some force to this that would cancel that out. But here's the problem. So if I'm moving from here to here, is there some other force that I can add that would somehow, cancel out that additional force? Or that, not really that additional force, that additional rotation? And there really isn't. I can't just add another force. And the reason for that is that, yes, I could calculate, okay, well, what if I added a different force at that same location and then figured it out in such a clever way that it would cancel out the change in rotational tendencies when I moved it from here to here. I could probably do that. It could be done mathematically. But the problem with that, if I add another force, then I'm going to have, but if I add another force, suddenly this thing is going to be translating differently. And what I really want to do is I want to move the force to a different location without changing either its rotational or its translational tendencies. So I cannot just add another force. cannot simply add a force, a second force, to supplement the moment, or to address the changed moment, or the changed rotational tendency. As this would alter the translation, the translational behavior. So, well, I can't just add another force. So what else can I do? If only there were a way to make something. See, when I'm moving this from here to here, I like how it's translating. I like that. I like that I'm not changing anything in terms of its translation. Its translational behaviors are not changed when I move this from here to here. Is there some other way that I can alter its rotation but without altering its translation? See, again, if I move this from here to here, the translation is fine. I don't want to mess with the rotation. If I try to add another force to sort of counteract the change in its rotation, well, then that added force is then going to also alter the translation, and my perfect translational balance is now all screwed up. So what I would really like to do is there somehow that I can go and alter just the rotation, because only the rotation has a problem when I move a force from one location to another. Is there some way I can do that? And, well, if you've probably figured it out by now, the way to do that is couples. Or a couple. Couples will save us. Or a couple will save us. So, again, a couple is a pure rotation. A couple is a pure rotation. Or a pure rotational tendency. It does not cause any translational effect on an object. 0 translational tendency. Did I say rotation? Oh, sorry. 0 translational effects on an object. So what I want to do is, if I have a body, let's say I have a body, I'll just draw two. Now I'm not going to try to make all the wavy lines look about the same, but let's just say I have two bodies, and just trust me on this that these are the same body. So what I want to do is, let's say I'm going to turn this into this. Let's say I originally had a force. Let's call this a force F. Actually, let me just label this in different colors here. I think I'll do that. Let's say I have point A and point B, a different point B. Let's make it way over here, for example. And then A, same B. So, initially I have a force at A, and this object has a certain tendency to rotate, translate, etc. But and this is force F, and I want to find an equivalent system with a force at B. Now the force is going to be the same. The force vector is going to be exactly the same, but if I want to move this from A to B, what I need to do is I need to add a couple. And that couple is going to behave in this force couple system, this moment vector, this couple, is going to behave exactly the same as this. And in fact, I should probably make this a two-way arrow to show that we could go back and forth on these. So originally we had a force at A, and then later, or the transformed, or the equivalent is the same force at A, same force at B, I should say, and with a couple to cancel out the change in moment, or to compensate for the change in moment, or the change in rotation. Because again, when we move the force from here to here, it causes a change in the rotational behavior, so we're going to add a couple to cancel it out essentially. For change rotational behavior. And at first this might seem rather difficult, but really this isn't too bad. To find an equivalent force couple system, it's really not too bad actually. It takes a while to explain the basic logic as I've done, and hopefully you have some understanding of now of what it is. But who knows? It might be clear as mud. So, to find an equivalent force couple system, one, the equivalent force remains unchanged. The equivalent force remains unchanged. So we're just going to pick it up and move it, no change. However, the moment, or the couple, the vector of the couple is found as follows. So let's say you had point A here and point B, and then you had, let's see, F here, and F originally was at A, and we picked it up and hauled it over to B, and we have this moment M, this couple M. Well, I'm going to define a vector R, and that R, I'll just call that AB. I didn't quite hit that arrow, but that's okay. At that point. Actually, I don't like that. Let's do that right. Okay, better. I'm going to say that's RAB. Now, technically, you don't have to use the, just like we've looked at previously with moments, you don't technically have to use the vector from the point that it was at to the point that you're moving it to, but usually that's the easiest to do. So, the moment, or the moment vector of the couple, moment vector of couple is going to simply be R cross F. Oh, there's the F here, F, and F. The moment vector of the couple M will be equal to RAB cross F. RAB crossed into the force vector. So basically, originally you had a force vector, F at A. This is what you had originally, and this is equivalent to a system made of two things: the force F at B and a moment vector who is equal to RAB cross F. Cross F here. Oh, RAB cross F, not just RA cross F. Alright, so I think next we're going to go work through a very simple example illustrating how you can do this. Sometimes having some numbers helps. So, for a minute, let's just consider a basic example. Share this. It's a shame this isn't a chemistry class, and I could make all sorts of jokes about basic examples. Because get it? Basic. Oh boy, I shouldn't quit my day job. Okay, so anyway, interestingly enough, I am quitting my day job. I'm going to go be a PhD student off at Oregon State, so that's neither here nor there. Okay, so we have X, Y, and Z, our X, Y, and Z axis. And let's say we have points A and B. Oh, and let's make this a little bit interesting. Let's say point A has coordinates -1 meter, -1 meter, and then in the Y, 1 meter, and the Z, -1 meter, why not? And then B, let's give this coordinates of 2 meters in the x, negative 2 meters, oh, that'll be too boring, negative 3 meters in the y, and in the z, let's say that's 2 meters as well. Okay, so originally, and then I have a force, and I'm just going to go ahead and give us the force vector. I think at this point you're good with working through force vectors. Force vector F, let's say this is, oh, I don't know, 3 newtons, comma, let's say 2 newtons in the y and negative 2 newtons in the z. You know, yeah, that'll work. Negative 2 newtons in the z. And so all this is given. All this is given here. And I want to find an equivalent force couple system at B. System at point B. And as far as why you'd want to do this, well, there's many reasons why you might want to do this. Where this might be particularly useful, though, is imagine I had a whole series of forces. Like, imagine I had a whole bunch of forces, like, you know, a dozen different forces. Now, I'm not going to do that for the sake of brevity in these videos, but let's say I had a whole bunch of forces on this, and I wanted to know what is the equivalent of all of those. So I could do this equivalent force couple system, basically moving everything to B, and then I could just add up all the forces and add up all the moment vectors together, and I could replace a dozen individual forces with a single force and a single couple located at B if I wanted to. And basically, if I had a whole bunch of forces all acting on one body, that would be a very easy way of collapsing it down to something much simpler and much easier to handle. Okay, so let's go ahead and get the R from A to B. This one's not going to be too bad. So R from A to B then. Well, let's go ahead and draw this, if I can manage to draw a straight line, which is always a little difficult, and, well, for me anyway. RAB. And then RAB, this is just going to be, let's just do this in vector form or vector notation. So, well, not IJK, just a little bracket notation. So in the x, as we go from negative 1 to 2, that's going to be 3 meters. As we go from 1 to negative 3, that's going to be negative 4 meters. And as we go from negative 1 to 2, that's going to be positive 3 meters. And the force is going to be the same. So the force vector at B is just going to be exactly the same. 3 newtons, comma 2 newtons, comma negative 2 newtons. That's not going to change. And, or however, the moment vector is going to be RAB cross F. So that's going to be then, let's see, that will be our 3 comma negative 4 comma 3 crossed into, and then let me just put meters, and 3 newtons, comma 2 newtons, comma negative 2 newtons. And I'm feeling lazy tonight, so I'm just going to throw that into my calculator and let it chug on the cross product. I think by now you know how to do a cross product. So 3, negative 4, 3, and then 3 to negative 2. Let's see, negative 2, enter that vector, and I'm just going to throw this in my little 89 here. Alright, so second math matrix, vector ops, and my cross product. And I'm going to do 3, negative 4, 3, crossed into 3 to negative 2. And I get 2, 15, 18. So again, I'm feeling a little lazy, so we'll just do this as a calculator cross product. 2 Newton meters, comma, 15 Newton meters, comma, 18 Newton meters. So in other words, what I could say is an equivalent force couple system is as follows. Basically, I have a force that's in the same direction of F is equal to 3 newtons comma 2 newtons, comma negative 2 newtons. But then I have a moment vector, and I should show everything here being, I guess, positive, but more positive in the z and y than in the x. So maybe something kind of like this. A moment vector, and maybe I'll show a little rotation around that. Moment vector. Maybe make this nice straightish. I cannot draw a straight line tonight. Oh well. Hey, I can't draw a straight line. Okay. Which is, I suppose, always. So then the moment vector is 2 Newton meters, comma 15 Newton meters, comma 18 Newton meters. So we have 2 Newton meters, 15 Newton meters, and 18 Newton meters. And so in the purple here, this is my final result. In the purple, this force and this moment is equivalent, this force and this couple is equivalent to this force vector. Again, this force and this couple is at B is equivalent to the force at A. So in other words, if I had a body connecting these 2 points, a single body connecting both of these points, or that was at both of these points was embedded in, this force at F would have the same effect on its behavior as this couple and this force applied at B. And really, that is the basic idea of finding equivalent force couple systems. We could look at more variations of this, but really, they would all come down to that. So there's that. That's the basic idea of equivalent force couple systems. Oftentimes, you see this in things like beam design. You see couples applied to beams a lot. In cases where you're, especially in frameworks where you have beam, one column, maybe like a column applying a bending moment to a beam at a point, that sort of thing. Very common indeed. But anyway, that may be a bit beyond the scope of where we're at right now. Okay, I think that'll do for part 3 of this lecture. I think that'll cover the last of what I want to cover for this lecture. Let me know if you have any questions. Again, in this lecture we've looked at couples, we've looked at what they are, we looked at how to find them in both scalar and vector forms, and we've looked now at how to find equivalent force couple systems. So please let me know if you have any questions. I'll always be available in class if you need me. I'll accept online class, but feel free to email me then. So hope you've found this a bit enjoyable. Hope you've learned a few things. Hope you've learned a bit about couples and their various properties. I hope you've learned and enjoyed, etc., etc., etc. And of course, let me know if you have any questions. If not, I will see you all for lecture 7 soon enough. We'll be looking at rigid body equilibrium. All right, I'm Tanya Larson. That will do it for now. And again, let me know if you have any questions. Please contact me here or through my email. And if not, I will see you all again for lecture 7 and other lectures in the future. And as always, thank you.